In this video, we're going to talk about energy. And energy is a word that we use a lot. We've got energy drinks. We've got people that are high energy. We've got people that are low energy. We've got energy concerns with gasoline. We know that if you eat food, it gives you energy. But we really don't know, or maybe you don't know, what energy is. So the definition the science book will give is this. The book tells us that energy is the ability to do work or produce heat. So I'll say that again. It's the ability to do work or produce heat. So what is work? What is work? We talk about homework. We talk about work hours. And work in a science context is pushing or pulling an object a certain distance. If you do that, you do work on the object. So if I push a box across the table in the chemistry room, I've done work on the box. I can give energy to that box. You can think about if I lift the box up, I give it and put it on a higher shelf, I've done work on it. You can also do energy to produce heat. If you rub your hands together, that energy that you're putting into rubbing your hands together makes the heat between the hands increase. So these are just some examples of everyday energy work connection. Okay, so what does this have to do with chemistry? Well, first let's define the two most important kinds of energy. So our first kind of energy is the energy of motion, and that's called kinetic energy. At New Trier, we know that there is a kinetic wellness department. We also know that there's a dance group called kinesis. Those both come from the same root, kina, which means motion. So the kinetic energy of motion is called the energy of motion is called the kinetic energy. Potential energy is the energy of position. And we'll talk about both of these. But you can see here in our picture on the side, this is from your book, chapter 10, that the ball A is higher than the ball B. So we would say ball A has more potential energy than ball B. If this person here looks like me with more hair, let's go with ball A, it will move. Ball B will not move because it has no potential energy, but ball A does. As ball A moves down the hill, its energy will change from potential to kinetic, and that is called the conservation of energy. As it loses one type of energy, it must gain another. All right, so that's the idea of kinetic and potential energy, and that's what they mean in the realm of science. And we'll talk in the next slide about how to use them in chemistry. So let's take a look at how energy and work are related in a different way, and this involves my favorite Hunger Games character, and that is Katniss Everdeen, as she aims her arrow at Peeta to shoot an arrow through his heart to show her that she loves him. And let's talk about what's happening in this picture. And this is from the movie. If you haven't seen the Hunger Games, she is a zombie that is attacking. She's not. No, different movie. Anyways, in the movie Hunger Games, Katniss will pull back on the string of the bow. Now, if you've ever done archery, you know that pulling back that string requires energy. So she supplies the energy and does work. Remember, work is a push or a pull, which pulls the string and the arrow back this distance. So I can draw on here. Let's do it in black. She pulls the arrow back this distance, D, which means she has done work on the arrow, we say in science terms. So she has applied energy. Her arm here has applied the energy to the bow to pull it back, to do work on the arrow. And now this arrow has one of the two types of energies that we talked about in the last slide. It has potential energy. Because she did work on it, it gained energy, and now it has potential energy. If she lets go, or when she lets go, the potential energy in the string will decrease as the arrow gains kinetic energy. And this is the idea known as conservation of energy. And that idea is that energy can go from potential to kinetic or kinetic to potential. And in this case, as the arrow is released, it's going to go from potential energy to kinetic energy. All right, the next, last idea in this video I want to take a look at is something called state functions. And in this unit, Unit 10, energy is a state function, and I want to explain what that is. And here's a familiar example to you. This is the Northfield campus, and I want you to imagine that you are going to go from the sidewalk here up to the first floor, the first level, right? There are two ways that you could go. Let's say that there was a rope hanging down, and you could climb the rope up and then be on the first floor. Or you could take the stairs all the way up here and then go around and then walk and end up right here. So you're going to go from this point here on the sidewalk to this point here on the first floor, right? So the two properties that I want to talk about are the distance traveled, so your distance traveled, and your change in height or your change in elevation. One of these is a state function, one of these isn't. If you think about the elevation, no matter which way you travel, whether you climb a rope and go straight up, or you climb the stairs and you go around, and maybe you go up and visit your old English teacher or your old English, I don't know where they're at, but maybe they're here, and then you go back and you end up here. No matter what path you took to get there, your change in elevation will be the same. Sorry, my Twitter's blowing up. Your change in elevation will be the same, and so that means that elevation is a state function. Distance traveled in this example is not a state function. Climbing the rope from here to here is a much shorter distance than walking all the way around. And so the path or the way that you make your trip does matter when it comes to distance. And so in that case, distance is a state function. I'll give you a second. Can you think of a couple other state functions, properties in real life that the path or the way you get to from point A to point B doesn't matter? Take a second and think about it, and we'll finish the video. All right, it might be a little tricky concept here, but if we were to talk about time traveled, would that be a state function? And if you said no, you're right, and you understand the concept, because if I were to drive along a road, the time it takes me does depend on the path. And we look at our definition of state function, it is something that is independent of its pathway. And so the state function we're going to use in chemistry is not elevation, which is a state function, or change in elevation, but it's energy. Okay, so that's it for this video. Have fun watching it. If you have any questions, put them in your whisk, bring them to class, and I'll copy tomorrow.